I'm very happy to introduce. David Clement, who is visiting us for a couple of days. So David did his PhD with the Nobel awardee in Alan Aspect in diasphydotic in we don't know, maybe 2017, let's say, 27. Yeah, we're not sure. But it should be around 27, and he's worked on the first experimental demonstrations of Anderson localization obtained with cold diodes. Then he moved to Florence for his postdoc, and he later joined diasphydotic as a professor, and now he has his own experimental setup where he's doing beautiful experiments with that we will see about today. So David, we are very happy to have you today, and please.
Thanks. So good morning, well, good afternoon, everyone. Actually, that's the first time I give a seminar just having eaten the pizza before, and I guess I will enjoy it. So, as Giuseppe said, I'm working at Institut d'Optique. So for those of you who do not know it, it's just south of Paris, so in the Paris area. And I will be reporting today about some studies of what we call strongly correlated bosons, so in a gas of interacting ultra-cold atoms. So let me just if this wants to go. Yes. So as in any experimental work, the work is mainly done by the people who are younger than me. So this is a picture of the students who participated to this work. So there were two previous PhD students, Gaëtan and Antoine, and these two guys, Maxime and Yann-Philippe, are the main driving force on the results I will be reporting. And we have strong theory support from Thomas de Rothschilde, who is in Lyon. So our team, the name is Latticilium, you will understand soon why, is part of the quantum gas group at Institut d'Optique, so which is the group created by Alain Aspect, and we have 6 different quantum gas experiments with some postdocs positions which are open. So if you are interested, please contact me to discuss. Okay, so I said I would talk about strongly correlated systems. So let me just start with what we have in electronic material, where this name strongly correlated has been used many times. So I give you here 2 examples: ITC superconductors and frustrating magnets that we all know. And there is one thing which happens in these systems is that you have some phase diagrams which are very rich. They have many phases and some, let's say, emergent properties at macroscopic level with very, let's say, nice properties, such as superconductors, for instance, which are relatively difficult to understand from a microscopic point of view. And the difficulty stems, as far as I understand, from this is not working well up. This difficulty is really coming from some interplay that you have at the microscopic level that are difficult to describe. So just so of course you have, let's say, frustration, for instance, if you talk about magnetism, but also some other type of interplay, which I think is nicely illustrated here in a recent work on, so this is on ultra-cold atoms, where what you have here in blue and red are 2 fermions, so 2 spins, opposite spins. And you have these 2 ladders where 2 holes have been created. And what you start doing is you move a hole. And so what happened, as it is depicted here, is that you are now having somehow the wrong magnetic texture, right? Because you want to be an antiferromagnet at low temperatures. So the second hole will be moving in order to recover the magnetic texture that you would like to have in order to lower the energy of the system. So if you move a charge, then you have an interplay between this kinetic, this charge transport, and magnetism. And these interplays are really difficult to understand. And especially, you cannot use theories where you linearize quantum fluctuations, or let's say use quasi-particle pictures, such as Landau-Fermi theory or BCS theory, to describe this kind of strongly correlated materials. So this is the reason why we call them strongly correlated, is that you need to go beyond linearized theory and include correlations which are non-Gaussian in order to describe the system. Right, so now there are not only electronic materials that can be strongly correlated, you have also some electron-photon system, for instance, and there's a nice review here with like many different phases and material where this type of strongly correlated matter can be found. And you can also obtain some strongly correlated matter in a gas of interacting bosons. And so this is the case that I will discuss today. And the question is whether how to describe a strongly interacting Bose gas. Are there some strong correlations, so in the form of non-Gaussian correlation? And if yes, how do they emerge? So this is the simple question to raise, and I would like to discuss that. So I will it will go as follows. I will first give you some short reminder about a weakly interacting Bose gas. So this is Bogoliubov theory, which I guess you all know. Tell you about our experimental setup and how we managed to be able to actually probe these correlation associated to the weakly interacting system. And these are of Gaussian nature. And then in the last part, I will tell you about our recent observation of non-Gaussian correlations in not in the weakly interacting regime, but in a strongly interacting regime. Okay, so well, you know about the emergence, I mean the appearance of Bogoliubov theory, which was related to the observation of superfluidity in liquid helium, so back like 1 century ago almost. And so this is this paper of Bogoliubov from '46, and what is predicted by this paper. If I stand here, is it better? Is that you have mainly, let's say, two consequences. The first one is that you have a linear spectrum of excitations at low momenta, and so this is actually a measurement made in a gas of ultra-cold atoms in like 20 years ago, where you have this linear part of the spectrum here at low momenta, and this is the origin of the superfluid character in an interacting gas of bosons. The other prediction is about the many-body ground state, and you have here also a recent verification of this prediction, where what is plotted here is the fraction of atoms which are in the fraction of atoms which are not depleted by interactions as a function of interaction strength, and let's say the scaling and the amplitude of this depletion in the many-body ground state was verified. So let me discuss a little bit this second part now, how one can do. So let's start with a non-interacting Bose gas. The Hamiltonian is very simple. You have a trap and some kinetic energy. And I would like to describe what happens in the momentum space. So of course, the ground state here for non-interacting boson is a Bose-Einstein condensate. And if you look at what is the density in momentum space, what you have is a peak, a delta function centered at k equals 0. It's a pure BEC. What Bogoliubov theory tells you is that if now I add interactions here, then this picture will break somehow. And the first hint you can have about it is that the interaction part is not commuting with a non-interacting Hamiltonian, so you will have quantum fluctuations, which are induced by interactions. And what happens is that you have the appearance of non-zero momenta, which we name quantum depletion. So just because it depletes the BEC to populate some non-zero moment. And just giving you this reference, which I think is really nice, is that you can obtain this result of quantum fluctuation just by using like some generalized Heisenberg inequalities, which is a really neat way to see it. Okay, so to go a little bit further, let's look at what type of interaction potential we can have. And in the ultra-cold regime, we can approximate the interaction as a two-body contact interaction. And because I want to play in momentum space, I rewrite this interaction term, this contact interaction, in the momentum space. And so this involves 4 operators. So this is the destruction of a a particle at momentum k2, destruction k1, and these are creation operators. And so this is a four-wave mixing process where you have, let's say, one mode at k1 and one mode at k2 that interact and then gives rise to outgoing modes at k1, let's say, plus k3, and this one will be k2 minus k3 because you need to conserve momentum. So the way to describe contact interaction is through four-wave mixing processes in momentum space. So let's go back to Bogoliubov theory. What Bogoliubov proposed is to consider the weakly interacting system where the BEC, the ground state without interaction, is depleted only by a tiny bit. So it means that the number of atoms in the BEC is close to the total number of atoms, and you replace these operators just by a C number. And so we will put that into this interaction term here. So at the largest order, you take all these guys being 0, so being in the BEC, and what you have is just interactions within the BEC. It typically gives rise to the mean field interaction term. And the next order, which is the one described by Bogoliubov theory, is where you consider two of these operators being in the BEC. So like you have two incoming BEC atoms colliding, and then they go outside the BEC, right, by this quantum fluctuation. And then what you have, because these two are 0, you have k and minus k for the outcoming modes. So in other words, Bogoliubov description of the quantum depletion of the BEC corresponds to the population of modes by pairs at opposite momentum. And let me stress that this corresponds to linearizing this interaction Hamiltonian. Okay, so this is linear description of quantum fluctuations. Okay, and so this is the first thing I would like to tell you, how one can probe and how we do that in our experiment. So we work with an ultra-cold gas, which is a bit peculiar in the field. We work with metastable helium atoms. So there are only a few experiments in the world doing that. And so this is a sketch of the bosonic species, so helium-4. Here you have the true ground state, and here you have a metastable state. And actually we produce ultra-cold gases here in this metastable state. Well, one of the reasons is because here we have the lasers that allows us to laser cool the gas and so on. But there is one thing which is very peculiar about this metastable state here, is that it has a huge internal energy. And this is because you are working with a noble gas, and so in its ground state you have like the electronic shell which is filled and it does not want to be excited. So you need to pay a lot of energy actually to excite it. But now the good thing is that if you are able to make a quantum gas here in this state, each atom has an internal energy which is about 20 eV, which is huge. It's like a small bomb. And especially if you have the atoms which are initially trapped here in these red arrows that represents lasers, and at some time you switch off the lasers to let the atom fall under gravity. If beneath, so it's rather long, yeah, it's half a meter, beneath we put a metallic plate. If you have a metastable atom that comes by a metallic surface, the atom can go to its true ground state, release the 20 eV of energy, and 20 eV is large enough to extract one electron from the metal. And so then the trick we play is we amplify this first electron in order to have a signal that we can detect. And by doing that, we can detect atoms one by one. On top of that, what we are doing is to be able to actually reveal the position in the XY plane of the detector and the time of arrival. So we have all three coordinates for each individual atom. So this is a real picture of the detector. This disc here, which is this, so it's not whatever metal, of course, it's a peculiar plate, but it has a diameter of 8 centimeters. So it's really like a macroscopic detection that we are doing. And now, you may, for those of you who are not familiar with, if you wait and if you let the atoms fall for a very long time of flight, what we call time of flight, to reach the detector, the final position is actually given by the initial velocity of the atom. Its initial position in the trap does not count. Just to give you a number, the typical size of a trap cloud here, it's let's say 20 to 30 micron. And the size of 1 pixel we have, let's say on our detector, it's about the same, it's about 60 micron. So we have no information about the initial position in the trap of the atoms, but what we have is information about the initial velocity. So that what we can do is to measure atoms one by one in 3D in the momentum space. And so this is just to show you, to illustrate what the type of distribution that we measure. Here, each tiny blue dot is a single atom. So it's 3D, and what you see this type of patches here. This is because we have diffracted a coherent matter wave, a Bose-Einstein condensate, in a crystalline structure. And so what you see, these different patches are the crystal diffraction peak of this coherent matter wave in the crystalline structure. Okay, so we use a crystal. And what we are doing is actually to load our ultra-cold atoms in a three-dimensional cubic structure. So this is made by standing laser beams. And this effectively realizes the Bose-Barth Hamiltonian, where you have a crystal structure, and that you can describe by considering the possibility for the atom to jump from one side to the other with a tunnel amplitude J. And when two atoms are on the same side, they repulsively interact with an interaction U. So the reason why we use this optical lattice, this crystal, is twofold. The first one is the fact that I told you that we want to measure the momentum in the trap after this long time of flight dynamics, and this you can do only if you have a ballistic expansion, so no interactions during the time of flight. And so the lattice allows us to ensure that, and actually this we verified some years ago now with our chairman here. He performed quantum Monte Carlo calculation in the trap of what should be the momentum distribution in the trap, and we compared that with the density in blue that we measure with our time of flight expansion and so on. So no description of the time of flight expansion in the theoretical calculation, and you see that there's a good match. And watch out that this is it's a semi-log scale, so the match is good over 4 orders of magnitude. Good. So we really measure what is in the trap in terms of momentum. The second reason to use the optical lattice is because we can play with the phase diagram of this Bose-Barth Hamiltonian, and especially it's easy to tune the ratio of the on-site interaction to the tunneling. So in order to go from a weakly interacting regime to a strongly interacting regime. So this is our experimental knob to change the regime of interactions. So I told you I would like to study strongly interacting bosons, and there is a simple way, well, an alternative way to increase the interaction in an ultra-cold Bose gas is to use so-called Feshbach resonances, which actually are used here on the experiment of Jean-Philippe with lithium. But there is one issue in the case of bosons, is that if you want to increase the interaction, you go close to what we call unitarity, and there you have large free body losses. So you are in a regime where you have a lot of losses if you want to crank up the interaction this way, and you also have some, let's say, free body physics, Efimov-like physics, which appears. So in order to avoid that, as I said, we will be working in an optical lattice. In this regime here, where we are far from the mode transition, so we are all in the superfluid regime, but here we can tune the interaction strength. And we can actually change, this is something which is similar to the condensate fraction, we can change the condensate fraction, so the regime of interactions, without losses and without free body physics kicks in to be in. Okay, so this set the stage. We have this single atom detection in momentum space, and we are able to tune the interaction strength to change the regime of interactions. Okay, so we first study as I said, I would like to convince you that we can probe the correlation associated to Bogoliubov, this correlation at opposite momenta. So we first look at an interaction strength which is relatively small, to be not too far from the weakly interacting regime. And so now this is a distribution that we measure on the experiment. So each tiny blue dot is a single atom and it's in the momentum space. So as I said before, you see these patches which are nothing but the condensate part of the gas, which is phase coherent and therefore diffracts coherently on the crystalline structure. So this is the condensate, and if I plot the density in momentum space as a function of momenta in the first Brillouin zone, well, you nicely see this peak here, which is this central one. So you only see these tiny atoms here, but they are. I mean, we can see it on the 3D picture. And if I plot the density in log scale, well, we see that there are some atoms there. Okay, so how to probe? What does it mean probing the fact that we have correlation between opposite momenta to probe the Bogoliubov picture? Well, it's really simple. You take one atom here, and then you wonder what is the conditional probability, knowing that I have one atom here, to get another one at minus k. So it's just like really simple to compute, and this is what we are doing. So we compute these conditional probabilities. For those of you who are more familiar with this normalized correlation function from, let's say, quantum optics, this is what it's a G2 function that we can plot here as a function of k plus k prime. And you see that there is a nice peak appearing here, located at k prime equals minus k. So it means that if I detect a particle at k, and I look at the conditional probability to get a particle at k prime, the maximum is located at minus k. So which is, you have strong correlation between k and minus k. So the first hint that this is not, let's say, some weird effect is that if we repeat this experiment in the case of a BEC that we have heated up with temperature, and here you look at the log scale, the density in the depletion has increased a lot, more than 1 order of magnitude, but this is a thermal effect, okay? It has nothing to do with quantum fluctuations. And if we compute again this G2 function in this red case, we don't see anything. So we have lost this correlation signal if we increase the temperature. There is another test that one can do, which is, coming back to our three-dimensional distribution, we can wonder about conditional probabilities, or G2 function, not at opposite momenta, but at close-by momenta. So if I detect one atom here, what is the probability to detect another one next by? And here I'm plotting this probability. You see there's a peak at k primes equal k now. And it is clear that this peak is not affected by temperature. So this is the same data set as before, the low temperature one in blue and the high temperature one in red. And so this is nothing but the bosonic bunching. So it only depends on the statistics of bosons, and whether they are cold or hot, they are still bosons. And so you still see this bunching peak. And so this is really in contrast with what you look on the very same data set, so blue and red and red. Here in the pairing mechanism, this is strongly affected by temperature, and this is therefore a signature of this quantum fluctuation that are present at zero temperature and which are predicted by Bogoliubov theory. Okay. So we also studied a bit the properties in order to convince ourselves that this was the correct signal. And actually, you can, just to make a long story short, if you are familiar with four-wave mixing in optics, typically what we have verified in our experiment is that we have exactly the same properties as two-mode squeeze states. So the kind of, let's say, the kind of scaling of the amplitude of the correlation with the population of the modes, of the fact that we have some relative number squeezing between the two modes, right? If you have n particles there, you have also close to n at minus k. And as you may already know, these two-mode squeeze state, they are Gaussian, right? There is nothing which is non-Gaussian in all what I've been discussing thus far. And so this is the weakly interacting regime. Good. So now I would like to go to the more interesting part and discuss what happens if we increase the interactions. So, coming back to Bose-Lyubov, I've been talking about the four-wave mixing process and the fact that we have a correlation between modes at opposite momenta that we have also revealed in the experiment. So now the question is, what is beyond Bose-Lyubov approximation in this picture? Well, the thing that you need to do is to look at the third order term where you have only one BEC atom interacting with a non-zero, with an atom in a mode at non-zero momenta. So let's say K1 for instance, and here, well, you get two outcoming modes and well, there is nothing much to be said. Well, actually there is something very simple to do is, well, K1, if I'm zero temperature, came from a first scattering process. So let me write the first scattering process. So two atoms in the BEC that create K1 minus K1. And then what you are left with is three atoms whose total sum is equal to 0. This is just momentum conservation. So in order to describe this third order term, actually this third order term comes after a first scattering between two BEC atoms, and this leads you to a triplet whose total sum is 0, which is exactly the analog of having a pair with a total sum equal to 0 for K minus K. And of course you directly see that I can keep going on with this picture, and if I look at the fourth order term, which means all non-zero particle colliding, K1, K2, then this guy had a partner minus K2, this guy had a partner minus K1, and what I'm left with is a quadruplet whose total sum is equal to 0. So this picture in the momentum space is really easy. What should be the beyond Bose-Lyubov correlations in an interacting Bose gas? And so the question we asked ourselves was, well, are these triplets, quadruplets, and so on present at equilibrium? Because this is like a microscopic picture of a single scattering event. It does not tell me what is the state of the equilibrium Bose gas. And are we able to reveal them somehow in the experiment? Okay, so I will slightly change the way I want to probe these correlated subsets and introduce connected correlations. So what are connected correlations? It's really easy, and let me tell you about on these pairing modes what it is. So what I've been discussing thus far is the total correlation, let's say at K and minus K, this guy here. And actually I've shown you a normalized version of it, but it's the same. So connected correlation means I want to remove from all the coincidences count the contribution of uncorrelated particles. So in order to build the two-body connected correlation, I need to subtract to the total number of coincidences the product of the densities. And actually this is exactly, it's similar to what we have done somehow, because if you want to have a positive connected two-body correlation, this amounts to having this normalized correlation I've shown you larger than 1. And you remember I've shown you this graph here. I told you that there's a peak here. So the connected part is this part here. And of course the product is what you have below 1. So it's exactly the same thing. But there is one good aspect about this quantity here, is that if you increase the number of pairs, this will increase. While if you normalize, so if you use a small G2, then you normalize but what happened in the density, and so you may not have a clear picture of how the number of pairs varies when you change interaction. So this is why, because we now want to go from the weakly to the strongly interacting regime and look at this pairing signal, we want to directly look at the number of pairs. Okay, and so what Bose-Lyubov tells me is that this connected part is associated to this anomalous correlator here, K minus K. Right? Just the probability to produce a pair at K and minus K. Okay, so so this is what we are doing now. We will be changing this ratio U over J to change the interaction strength. And so let me show you the two-body connected correlation that we measure. So this is the two-body connected correlation. With the 0 here stands from the fact that we are looking for a total sum equal to 0 as a function of the interaction strength. So increasing interaction strength means increasing the quantum depletion, and this is what we observe. So at weak interactions, what we observe, this increase here is compatible with Bogoliubov theory. And so it's compatible with some, let's say, numerics from this paper, but the picture is really simple. In Bogoliubov theory, all the depletion of the BEC comes by producing pairs k minus k. So if you increase the total depletion of the BEC, it means that you have increased the number of pairs, because you only deplete the BEC by creating pairs. So it's really, really simple. But you see that we have a non-monotonic variation, which of course cannot be explained by Bogoliubov theory, which tells you that the number of pairs can only increase. So is this associated to beyond Bogoliubov? Well, so from a first, let's say, qualitative observation, one say yes, it should be, because we don't have in Bogoliubov approach anything that allows you to decrease the number of pairs while increasing the amount of quantum depletion. But we have also our colleague Tommaso Rochilde from Lyon, who actually performed similar calculation. So here you have also the connected two-body correlation at k minus k, which is plotted as a function of an interaction strength. But for a model, which is a lattice model, a bit different from the one we use in the experiment, it's a so-called quantum rotor model. And the good thing about this quantum rotor model is that it includes quantum fluctuations beyond linear approximation. So beyond the linearized approximation of Bogoliubov. And what he finds is that indeed this connected two-body connected term first increases and then start to decrease very similarly to what we have in the experiment. Okay, and let me just point out one thing, which is, you see we have this maxima here, and it's kind of the same in the numerics, which happens, so now you have, instead of plotting u over j, I'm plotting here the condensate fraction, so it decreases from 1 to some values. This maxima here happens at a condensate fraction of 0.75, which means that you really have a macroscopic BEC. But already in a macroscopic BEC, Bogoliubov theory is not enough to capture all the correlations, and you really need to go beyond Bogoliubov theory. And so here, what we say is that Bogoliubov theory does not work, and we enter, therefore, the strongly correlated regime, where we need to include quantum fluctuations beyond linearized. Okay? So, now we have been talking about connected correlation. What about triplets? Because I said that triplets would appear. So, in the experiment, we have not been able to identify some triplets. Well, in the numerics, Tommaso managed to identify some triplets. So here you have the connected free-body correlations, which is plotted on the same scale here. And you see that indeed they also increase. So you also have triplets with total momentum equal to 0. Their amplitude is typically 1 order of magnitude smaller. And we believe that this is the main reason why we have difficulty in the experiment to identify them. But it's clear why the amplitude is small. Because one has to remember that a triplet comes from an initial pair with one of the partners of the pair colliding with a BEC. So it means that the signal of correlation you have from pairs then can go to triplet correlations, but you can combine this triplet in any modes of the momentum space, because you have a new degree of freedom. So it means that the amplitude of correlations of triplet will be much smaller than that of pairs, just because you have many possibilities to create a triplet. So it makes triplets much more difficult to actually reveal in experiments. And so in some data set you have some hint that there could be, but it's really not sufficient in terms of signal to noise in order to...
Could it be that if you go to lower particle number, then you detect them better? Because
Yes. Well, it's not lower particle number, but I would rather say small system size. Because if you have a small system size, it means that the number of modes in momentum space is reduced, and so therefore you distribute the pairs in a smaller number of modes. Okay, and just to come back to this picture I was drawing before, one thing that we can also learn from the quantum rotor is that if we plot the amplitude, so the number of triplets normalized to the number of pairs, what we see is that indeed the number of triplets increases. So at low values in the weakly interacting regime, you can neglect this term here where you create a triplet, but as interaction increase, then you need to account for it. And a funny comment is that you see that the maximum of triplet is a bit at higher temperature, at higher interaction strength than the one of pairs, but not that much. And so the reason where the number of pairs and triplets then decrease is because when you start to populate triplet, you can also easily populate quadruplets and quintets and so on. And so you dilute the correlations you have in the weakly interacting regime, where they are all k minus k. But then as interaction increase, you dilute them in many kind of correlated n-uplets. And so therefore you cannot easily see them if you look at a single type of correlator. So one question we are very interested in is how to characterize this regime where correlation have been, let's say, distributed over all the k modes. Okay, so let me come back to the experiment to discuss one last thing. I have 5 minutes. Yeah. So in the experiment, you may have seen that we have observed this connected correlation to be negative. So in Bogoliubov approximation, it should be positive. This is clear because it's the number of k minus k. So what can we tell about that? And I would like to just come back to what is a fourth order connected correlator. So it means I'm involving four operators. And I would like to describe this connected part here in terms of all these guys. So it looks like a bit messy, but it's actually really simple to understand. So I'm interested in this connected four operator. And so how do I define that? Well, you take all possible correlations. So this is this one. There is not the small c that you have here. So you take all possible correlations, and then you subtract to all these correlations the contribution of all lower order ones. So what can you have in order to get a four coincidence count? Well, you can have a triplet plus one particle. You can have two pairs. You can have a pair plus two singlet, or you can have 4 times a singlet. So each line here corresponds to these different contributions, which are low order correlations. And if you look at so a singlet means an average of this A or A dagger operator. There is one thing which is great in the experiment is that we can look again at the local bunching, and what we see as a function of interaction is that it is always, the bunching amplitude is always compatible with 2, which means a perfectly contrasted bunching. And to get that, you need to have no field coherence. So of course you could tell me, well, you have no BEC in the depletion of the BEC and so on, so we could also put this type of argument, but I would say that there is this experimental evidence which then tells you that you can remove all these guys, because this is with the average of singlets. So this goes to 0, and you are left only with this possibility here. So it simplifies a lot. And this 4-point correlator minus this, which is nothing but the densities, this is the two-body connected correlation I've shown before. So that I can write this expression like that. The 4-point correlator is equal to the two-body connected correlation I've been plotted minus these two terms. And now it's clear that if I have this guy negative, because these two guys are also negative by definition, it means that I must have the connected 4-point correlator to be non-zero and negative. And if you have a 4-point correlator, a connected correlator, which is non-zero, it means that the statistics of the state is non-Gaussian. This is the definition. Because for any Gaussian states, connected correlators of order higher or equal to 3 are 0 by definition. Times is up. So this is a direct experimental proof without any, it's not theory dependent, but in the experiment we have signatures of non-Gaussian statistics, which appears when the system is strongly interacting. Okay, so times is up, and so I've told you about our past observation of these Bogoliubov pairing mechanisms, and the fact that it has the properties of a Gaussian state, analog to two-mode squeeze state, and that now, more recently, we have observed the need to go beyond Bogoliubov and to include nonlinear quantum fluctuations to explain that this connected two-body term is non-monotonous, and that we also have some direct evidence of these non-Gaussian correlations appearing in this strongly interacting Bose gas. And the nice thing about all this, I believe, is that it's really simple at a microscopic level to understand where from these non-Gaussian correlations appear in this momentum space. Okay, and with this, I thank you for your attention and will be very pleased to further discuss.
Thank you, David, for the nice seminar. Are there questions in the room? Lovely.
For very nice result. First, then for your momentum distribution you see at the beginning, in principle, at least what I know from fermions, you have a characteristic tail, which is 1 over k to the 4th power at high momentum, which is due to contact interaction. Do you also see that in data, and is it a similar type of correlations than the sort of k minus k that's created by quantum fluctuation? Because in principle it's the same, right?
So the first answer to your question is that the k to minus 4 tails that should appear due to contact interaction appear on a k scale which is larger than the first Brillouin zone. So actually we cannot see it in a lattice experiment because of that. Then the other thing that I would tell you is that indeed the k to minus 4, you can also get it from just applying Bogoliubov theory and looking at the vk's at large k's. But when you look at large k's, you're really looking at what happened, let's say, in the close by, in the trap, right? In the interacting potential of two atoms. And what we are interested in is not like the Bogoliubov spectrum at large k's. It's really the one at low k's, where this comes from, let's say, if you wish, phonon type of excitation. This really comes from having excitations which are delocalized over the gas. So it's not like only point-like, two-body physics. You really need the many-body BEC. Like if you wish, the other way of saying, another way of telling the same, is that if you would be able to really consider only one scattering event of two BEC atoms, then this strongly violates energy conservation. Okay? And the only way you can, let's say, think of it, so you cannot identify one scattering event, and the reason is because any atom in the BEC wave function can interact this way. And you really need to let's say, to consider the full many-body ground state in order not to say wrong statements.
Okay, thanks. There are more questions? Yeah.
Go ahead.
Right.
So you need to remove your traplet to switch off the lasers for electrons to be free and to fall on the plate according to the momentum distribution. When you do that, there is no problem with that. So you can do it fast enough, and when you switch off the lasers, you don't get additional distortion to the momentum distribution.
Yes, no, we do not. So the point is, let's say, I would say you have three energy scales. All the ones which are associated with the equilibrium of the Bose gas in the lattice, so J, U, the chemical potential, and so on. And all these are much smaller than the 0-point energy in a single lattice site. Okay? Which means that when you turn off the lattice, what drives the expansion is the expansion associated with a 0-point energy in a single lattice. And then the first energy scale, which is even larger, it's how fast we can switch off the crystalline structure. And this we can do that much faster than the time scale associated with the 0-point energy. So we can switch off very fast. Then the 0-point energy ensures that interactions and things like that do not count. And what we have seen is that indeed up to the, let's say, 10 to minus 4 in density, we are unable to see an effect of a non-ballistic dynamics during the time of flight.
I can explain why I asked. I'm doing unresolved photo emission spectroscopy, and we can only dream of switching off the ionic lattice.
Yes.
Yeah, beautiful experiment indeed. My question is a quite general nature. I mean, if I have an ultra-cold Bose gas, it would be surprising if there were no many-body effects or no correlation beyond Bogoliubov. I mean, we have all the quantum simulation experiments that match with the theory, also the very old predictions about the correction to TC, which is also many-body effect beyond Bogoliubov. So my question is, what do we specifically learn about quantum correlations beyond Bogoliubov from your experiment? I mean, is there some quantitative feature or some specific feature that we learn, or is it just a yes/no answer? Because
so it's well, it's a very fair question, and I would say that the main reason of conducting this experiment was just to test this type of very simple ideas. Okay. And just to see whether, with this simple picture, like, okay, I stand only at Bogoliubov, do I see that indeed there are some microscopic correlations? And you see the experiment I've shown in the very beginning, when the linear spectrum has been observed, the total depletion has been measured, all these are macroscopic quantities. We had not any clue before this experiment whether indeed at the microscopic level we have this type of, let's say, two-mode squeeze state. And building on that, the next question was, well, okay, now that we can see the two-mode squeeze state associated with Bogoliubov at the microscopic level, what can I tell about higher order still at the microscopic level? And so this is, I would say, rather to build a picture, a simple intuitive picture of what would happen at the microscopic level. But of course, we do not need, let's say, this in order to compute macroscopic correlation, microscopic quantities where we need to include beyond Bogoliubov effect.
I have a very short, thank you. I have a very short one. I mean, as you say, this is even the simplest case. It is a two-mode squeezed state, which is of course Gaussian, but it is also it is an entangled state. So
yes.
Given the very special laboratory you work in, I mean, have you ever considered running some Bell inequality measurements on these performances?
So that's a very good question, and so let me just answer on one part. So the first part of the question. So what is plotted here, it's the amplitude of correlation at k minus k, this is the green dots, and at kk, which is the local correlator. So here what you see is that we have a strong violation of Cauchy-Schwarz inequality because we observe correlation between modes, which is much larger than the local correlation. So if you would assume that the Bogoliubov theory describes that, which means that if you assume that there is no coherence between the mode at k and the mode at minus k, this difference between green and blue is already a proof, according to Orodeschi criteria, of entanglement. But of course, the issue is we don't want to rely on Bogoliubov, assuming Bogoliubov theory. We would like to measure the cross coherence between k and minus k. And this requires an interferometer type of experiment, which would go exactly in the direction that you are mentioning about belt tests on this type of pictures. So we have thought a lot about that. Well, we have some older colleague who knows a bit about Bell experiments, right? The issue is that we are working with about 100 atoms in the depletion of a BEC, and we have 10,000 modes in momentum space, which means that these pairs, you have a small number of pairs, and each shot they are in various modes. So building such an interferometer in this configuration is just hopeless. But coming back to the question before, if we now would reduce our experiment to, let's say, a small number of modes in momentum space, so a small size trap system, and most probably even better go to 2D or 1D to have only a few number of modes to compute, then we can think implementing this interference experiment and directly reveal the type of entanglement you're talking about.
But if you were to like compute the quantum Fisher information, because that maybe you can know because from the variance, and there you could detect some multipartite entanglement.
Well, let's discuss it, because so I have in mind one thing which about quantum Fisher, which is also the way I have let's say it in mind. It boils down to the same problem that we have only a few modes populating at each run of the experiment, but maybe there are smarter ways of what we have thought of. So that would be interesting to discuss.
I also had a general question about this the non-Gaussian correlation. Is it somehow related to those rich phase diagrams you showed in the very beginning? Like,
well, it's what I would say is that in this rich phase diagram, it's clear that you have also non-zero high-order connected correlations, non-Gaussian, but the mechanisms at microscopic level are completely different.
Okay, maybe one last question, or good? Okay, thank you very much, David. Thank you.